In this video, we are going to talk about the vector space of linear maps. This is our overview slide, which we'll spend about 5 minutes on before we go to the main part of our video, where we'll cover each of these topics in more detail and with more examples. We will start by defining a linear map, sometimes called a linear transformation, from a vector space V to another vector space W. And a linear map is a function, which we'll call T for transformation, that maps from V to W with the following properties. First, additivity holds. That is, the transformation on a vector U plus a vector V is equal to the sum of the transformation of the vector U plus the transformation on the vector V. And then second, homogeneity holds. That is, the transformation on a scalar A times the vector V is equal to A times the transformation on the vector V for all A scalars in F and the vector in the vector space. We will work this example as well as many others in the main part of the video. Now we look at the set of all linear maps from V to W, and we notate that with the script L. So we have our linear L for linear maps from V to W. We have this theorem, linear maps and the basis of domain. So suppose V1, V2 up to Vn is a basis for vector space V, and W1, W2 up to Wn are vectors in W. Then there exists a unique linear map, T going from V to W, such that T sub V sub j is equal to Wj. The example we will do for this leads us to this side note here. Once you know how a linear transformation acts on a basis of V, you know how the transformation acts on all vectors of V, since all vectors of V can be written as a linear combination of the basis vectors. Our last topic will be operations on linear maps from V to W. We can add our linear maps and we can multiply our linear maps. And it turns out with this definition of addition and scalar multiplication, our space of linear maps is a vector space. So the set of all linear maps from V to W form a vector space. We also can define the product of linear maps, which looks a lot like function composition. And then we have the algebraic properties of using this product of linear maps. And finally, we have the theorem that says linear maps always take the zero vector to the zero vector. That wraps up our overview, so we can come back and start again with linear maps and take a closer look at linear transformations. We will start with the definition of a linear map, also called a linear transformation. So a linear map from a vector space V to a vector space W is a function T. And we have this notation, T is a map from V to W, and if it's linear, it will have the following properties. One, it'll obey the additivity property, which is T times the sum of two vectors is equal to the sum of T of the first vector plus T of the second vector. The second property we have for linear maps is homogeneity, which is T times a scalar multiple A times a vector V. We can pull out the scalar multiple and then multiply it times T times the vector V. I like pictures, so I drew this picture here. We represent our first vector space V, which is our domain. Remember, T goes from V to W, as a blob, or a set. I shouldn't say a blob, but it's a set. So I have a circle around my set, and inside the circle are my vectors V1 and V2. Then we have this other vector space W. It's another set of vectors, W1, W2. And now we have our transformation T. So it'll pair up V1 with some vector in W, and it'll pair up V2 with some vector in W. So basically it pairs up everything in the domain with exactly one thing in W. And what we want to remember is functions are well defined. Every element of the domain is mapped to exactly one element in the range. And here we did say that our transformation is a function. The first example I have for you is let T be the transformation from R3 to R2. And we define that as T on our vector X, which is in R3, remember R3 is our domain, is equal to the two-dimensional vector, remember R2 is our range, x1 minus x2, that is the first coordinate minus the second coordinate of our R3 vector. And then the second coordinate of t of x is x2 minus x3. So we want to verify t is a linear transformation. This, by the way, is the example we did in the overview, but I'm going to do it with a few more details and pictures. So first, just to get a feel for this transformation, I'm going to do a small example. I'm going to take a vector u from R3. So I'm going to let u equal to 1, 2, 3, and I'm going to put it through my transformation t. So t of u is equal to x1 minus x2. That is my first coordinate minus second coordinate, 1 minus 2. And then my second coordinate is x2 minus x3. So that's my second coordinate minus my third coordinate, which is 2 minus 3. So you can see t takes this vector u and transforms it to the vector in R2, negative 1, negative 1. Here, using our set kind of picture, our domain, our v, is equal to R3. So we're taking vectors from R3, and we're mapping them over here to, u, which are vectors in R2. And in this case, our vector 1, 2, 3 gets mapped to the vector negative 1, negative 1. Now, if I want to show or verify that t is a linear transformation, the two things I need to show are additivity and homogeneity. Starting with additive identity, I want to see what happens when I transform a vector x plus a vector y. So x is in R3 and y is also in R3. So x is equal to x1, x2, x3, y is equal to y1, y2, y3. So when we add them together, we get the vector with first coordinate x1 plus y1, second coordinate x2 plus y2, and last coordinate x3 plus y3. Now we want to put this vector here through our transformation. And our transformation says, and remember our transformation goes to R2, our first coordinate will be x1 minus x2. And remember at this point when I'm talking about my first coordinate, I'm talking about the coordinate in R2. And this x1 minus x2, these are coordinates from our R3 vector. That actually made it sound more difficult than it really should be. But my first coordinate is x1 minus x2. So in other words, over here on our R3 vector, we're going to get our first coordinate, x1 plus y1, and we're going to subtract our second coordinate, x2 plus y2. Our second coordinate for our resulting R2 vector is going to be x2 minus x3. So coming back here, x2 is equal to, our second coordinate is equal to x2 plus y2, and then I need my minus x3, that's x3 plus y3. So this is my transformation. The rest over here is algebra, which I have notated. We use the distributive law to distribute the negative sign. We associate, we group the x's together, the y's together, and then by property of vector addition, we separate out this vector, the x vector, from the y vector. And what you see, what we have is exactly the transformation of the x vector, and this over here is the transformation of the y vector. For homogeneity, we're going to look at the transformation of a scalar times a vector. So our vector, let's say that's equal with coordinates v1, v2, v3. A scalar times that vector will give us alpha v1, alpha v2, alpha v3. We plug this into our transformation, which is the first coordinate minus the second coordinate. So that's alpha v1 minus alpha v2. And then our second coordinate will be x2 minus x3. So that's alpha v2 minus alpha v3. The rest then is algebra. We use the distributive law to take out our alpha, and then by vector multiplication, vector scalar multiplication, we can take out our scalar, factor out our scalar, and this here is exactly alpha times our transformation of v. Now, since we have shown additivity and homogeneity, we can say that our transformation is linear. And I do want to take a look at this example before we leave it with this picture here. We had an x vector, with coordinates x1, x2, x3. We have a y vector with coordinates y1, y2, y3. And each of them are mapped over here onto the range by our transformation. So this will be t of x, and over here this is t of y. Over here in our R3 vector space, we can add x to vector y, and we get our x plus y vector. When we transform it according to our linear transformation, our result should be the same as if we add this vector, t of x plus t of y in this vector space. And that's what it means to be linear, as well as having the homogeneity property. Before we want to go on, I wanted to give you a mapping that is not linear. So I've already answered the question for you. But here we're going to let H be a mapping from R2 to R2. And H is defined as x1 minus x2 plus 1. And the second coordinate is 3x2. And to determine if H is linear, we're going to look at additivity and homogeneity. When I look at h of x plus y, that is h of x1 plus y1 and x2 plus y2, remember we're in R2, then I'm going to do x1 minus x2 plus 1. So our first coordinate is x1 plus y1. I subtract our second coordinate, x2 plus y2, and then I add 1. For the next coordinate of our range, that's 3x2. That's 3 times the second coordinate, so 3 times x2 plus y2. Algebraically, we can group our x's together, so we get x1 minus x2. We can group these y's together, so we get y1 minus y2, and then we have our plus 1. And below, we can group our 3x2 right under our x values for the first coordinate, and we'll group our 3y2 over here. So we can separate this out to x1 minus x2 plus 1 over 3x2. And then what we have left is our y1 minus y2 over 3y2. And you can see this is not equal to h of x. Well, actually, this part is good for h of x, right? We have our x1 minus x2 plus 1 over 3x2. It's this over here. This does not equal to h of y because we're missing that plus 1. So because this is not equal to h of x plus h of y, additivity does not hold, and therefore h is not a linear map. And this is enough to show that h is not a linear map. We do not have to do any more. I'm going to do more just to illustrate homogeneity also does not hold, but to show whether or not this is a linear map, any one of these conditions failing is enough, and you can stop. For homogeneity, we need to look at h of a scalar times x. So a scalar times our vector x is just alpha x1, alpha x2, and then applying our map of h, that's the first coordinate minus the second coordinate plus 1. So that's alpha x1 minus alpha x2 plus 1. And then for the second coordinate, that's 3x2. So 3 times alpha x2. Now, the problem with homogeneity here is that I cannot, like this looks kind of promising, that x1 minus x2 plus 1. It's sort of this form. But the thing is I want to pull out an alpha, and I can't factor an alpha out of this 1. So in other words, if I take a look at alpha h of x, that would be alpha times my h of x is equal to x1 minus x2 plus 1 over 3x2. And when I multiply it by alpha, I have this extra alpha that I don't have here. So these two are not equal, and therefore homogeneity does not hold, and H is not a linear map. Our next example is a transformation on polynomials of degree 2 or less to the real numbers. And our transformation of our polynomial is equal to the polynomial evaluated at 2. This here is an example of this transformation. So if our polynomial, we need a polynomial of degree 2 or less, so I chose x squared plus 1. So that is definitely in our space of polynomials degree 2 or less. So the transformation on this polynomial is equal to p of 2. So that'll be equal to 2 squared plus 1. It is equal to 5. So you can see t has taken this polynomial and given us a real number. To show that t is linear, we need to show additivity and homogeneity. So starting with additivity, I'm going to say, let's have two then polynomials of degree 2 or less. We'll call them p and q. The general form of p then is going to be a0 plus a1x plus a2x squared. For q, I chose coefficients named b. So b0 plus b1x plus b2x squared. Now I can take the transform of p plus q. So when I add these two polynomials, I'm going to have t of I'm going to add my coefficients first, a naught plus b naught, and then my a1 plus b1 x, and then a2 plus b2 x squared. So my transformation now is to plug in, for t of this polynomial, is to plug in 2 wherever x is. So I'm going to keep my a naught plus b naught. I'm going to have my a1 plus b1 times 2, because x is now equal to 2. And then I'm going to have my a2 plus b2 times 2 squared, which is, well, here I just put 2 squared, but it's 4 times a2 plus b2. Now I can group my a terms together, so I have my a naught, I have my 2a1, and I have my 4a squared. I can group my b terms together. I have my b naught plus 2b1 plus 4b squared. So here, this first polynomial in parentheses here is going to be, you can see that that's p of 2. If I plugged in 2 here into p of x, I would get this first polynomial. The second polynomial is now q of 2. So our t of p plus q is equal to t of p plus t of q. So we've shown additivity holds. To show homogeneity, I'm going to look at t of alpha times p. So alpha times p over here will give me an alpha a naught plus alpha a1x plus alpha a2 x squared. Now, plugging in my transformation now, which just plugs in the number 2 for everywhere we have x, we're going to get alpha a naught plus 2 alpha a1 plus 2 squared alpha a2. I can factor out my alpha, and I'll have alpha times a naught plus 2a1 plus 4a2, which this is exactly alpha, and this is p of 2. So that's alpha transpose of p. Therefore, homogeneity holds, and since we have additivity and homogeneity, that means t is a linear transform. At this time, this is back on our overview page. We've talked about linear maps and linear transforms. We're going to introduce this notation. So the set of all linear maps from vector space V to W is notated with this script L, VW. So the L is sort of stands for linear, a linear map from V to W. I have the notes on linear mapping here and the notation here for the set of all linear maps for your reference, and now we'll do another set of examples. The first example is the zero function. So let 0 denote the function that maps each element of some vector space to the additive identity of another space. To be specific, 0 in our set of functions from V to W and is defined as 0 when you plug in V is equal to the 0 vector. I have this set picture of what's going on. We have our vector space V, and we have another vector space W. In W, because it is a vector space, it must have a 0 element, an additive identity. And now what our 0 function does, it almost looks like an O, it maps everything in V to the 0 function. This line shouldn't be there. This was my illustration that O goes from V to W, but it actually looks like I should be more careful. It looks like something's being mapped to something other than 0. But this is for the function, mapping from V to W. But all the elements in V get mapped to the identity element in the vector space W. To show that this function is linear, first we need to show additivity. So our 0 function of u plus v is equal to 0. It maps to the 0 element. Well, the 0 element is equal to 0 plus 0. This first 0 is 0 of u, and the second 0 is 0 of v. So you can see additivity holds. Next, for homogeneity, we have the 0 of alpha u, which is equal to 0, because everything's equal to 0, which is equal to alpha times 0, which is equal to alpha times 0 of u. Therefore, since we have additivity and homogeneity, we have that the 0 function is linear. The next example is the identity function. Let the identity function, which we'll denote with a capital I, denote the function on some vector space that maps each element onto itself. To be specific, I is part of the linear maps from the vector space V to V. So it's the same vector space. It's not V to W or V to U. It's V to itself. And it's defined as I of V is equal to V. I have my set picture here. So we have my set V, and then we repeat the set V. So X then gets mapped to X, and Y gets mapped to Y. Everything gets mapped to itself. And I should put the little vector bar over both of these because these are vectors. To show the identity function is linear, we need to show additivity and homogeneity. So I of X plus Y is equal to itself, X plus Y, which is equal to I of X plus I of Y. So we have additivity, homogeneity, I of alpha X is equal to alpha X, which is equal to alpha I of X. Therefore, the identity function is linear. Our next example is the differentiation function on polynomials with real coefficients mapping to other polynomials with real coefficients. And we'll denote this as d of p is equal to p prime. So kind of a picture of what's going on over here. We have polynomials with real numbers that we plug in for x. So for example, we might have 4x squared plus 2. We might have 2x to the 4th, or 5x3 plus 25x. Our derivative function then maps this to another set of polynomials, and it maps it to p prime. So 4x squared plus 2 gets mapped to 8x. This 2x to the 4th, that'll also get mapped to 8x. Remember, it's okay to map things to the same range. It's just that you don't want to map any one element from the domain to two elements in the range. But you can map two elements from the domain to one element in the range. Here you have 5x cubed plus 25x. When you take the derivative, you get mapped to 15x squared plus 25. To show that differentiation over this polynomial space is linear, we need to show additivity and homogeneity. So I'm going to start with two polynomials, p and x. P is going to be a naught plus a1x plus a2x squared all the way up to anxn. And q of x is going to be b naught plus b1x plus b2x squared all the way up to bnx to the n. We start with additivity, so we're going to look at d of p plus q. So p plus q is going to be our a naught plus b naught, our a1 plus b1x, our a2 plus b2x squared, all the way up to an plus bn x to the n. And for the derivative function, we're going to take, I'm just going to indicate that with the prime. When we take the derivative, these are constants, so they go to 0. Here, this term becomes a1 plus b1. This term here, we get the 2x times a2 plus b2, all the way up to here we get the n, an plus bn, x to the n minus 1. We can then group our a terms together, our a1, our 2a2x, our, what do we have, an x to the n minus 1. We can group then our b terms together. That would be our b1, our 2b2x, and then our n bn x to the n minus 1. This first group of terms in this parentheses, that's just the derivative of p, whereas the second group of terms over here in the parentheses is the derivative of q. Therefore, our d of p plus q is equal to d of p plus d of q, and additivity holds. To look at homogeneity, let's consider the derivative of alpha times p. So alpha times p is alpha a naught plus alpha a1x plus alpha a2x squared all the way up to alpha an x to the n. And the derivative function, I just notate that with the prime over here. So taking the derivative, this is a constant, it goes to 0. This here is alpha a1. That's our first term from our derivative. Here we're going to have 2 alpha a2x. This is our next term. And then all the way down to n alpha an x to the n minus 1. Factoring out my alpha, I have alpha then a1 plus 2a2x all the way up to n a(n) x to the n minus 1. This term, or this factor inside the parentheses, is simply the derivative of our p. So what we have is alpha times our polynomial p, and therefore derivative of alpha of p is equal to alpha derivative of p. And therefore both additivity and homogeneity hold, and differentiation of polynomials then is linear. Our next example is integration. We're going to define our transform going from the polynomial space to a scalar, a real number, by t of our polynomial is equal to the integral from 0 to 1 of our polynomial dx. I have a quick example just to illustrate this. For one polynomial, let's say it's equal to 3x squared plus 2, then our transform of this polynomial is going to be the integral 0 to 1, 3x squared plus 2 dx. So when we do the integral, we get 6x evaluated at 1 and 0, which gives us 6. So in other words, we're going from this polynomial space, 3x squared plus 2, and after our integration here, we map to a real number, 6. To show this differentiation is linear, we have to show additivity and homogeneity. So we start with additivity by showing this transformation on polynomial p plus polynomial q. Well, first let's say that's equal to the integral from 0 to 1, the polynomial p plus polynomial q dx. But here, from properties of integration, we know we can separate this into two integrals. In other words, this integral here is equal to the integral of 0 to 1 p of x dx plus integral 0 to 1 q of x dx. But this first integral just happens to be t of p of x, and the second integral happens to be t q of x. So we've shown additivity holds. Next, we're going to show homogeneity. So we look at the transform on alpha p of x. So this is going to be the integral from 0 to 1 alpha p of x. But we know from properties of integration that we can factor out this scalar alpha. So we're going to have alpha integral from 0 to 1 p of x dx, but this integral is just equal to the transform on p of x. Since we have shown both additivity and homogeneity, then our transform t of p, which is equal to the integral 0 to 1 p of x dx, is a linear map. Next, we have multiplication by x squared. So our transform is a linear map from the space of polynomials to the space of polynomials. And our transform is given t of p of x is equal to x squared times our polynomial. So a quick example in what this looks like. Over here, we're in our space of polynomials, so something like x squared plus 2x. Now we're mapping to another polynomial, and what it is it's going to be x squared times p of x. So this polynomial would get multiplied by x squared. So that would be x to the fourth plus 2x cubed. Make sure that this is a fourth, x to the fourth, not x squared, plus 2x cubed. To show linearity, we're going to show additivity and homogeneity. We're going to start with two polynomials, p of x and q of x, and then we're going to take the transformation on p plus q. So the transformation, and here we have p plus q, that would be the a naught plus b naught, and then the a1 plus b1 times x, a2 plus b2 times x squared, and an times bn x to the n. And when we transform it, we're going to multiply our polynomial by x squared. So I have my a naught plus b naught x squared plus a1 plus b1 x cubed plus a2 plus b2 x to the fourth all the way to an plus bn x to the n plus 2. The next lines are just algebraic. Here I grouped together my a naught, a1, a2, and an terms. Here I grouped my b terms, b naught, b1, b2 up to bn. And then the next thing I did is I factored out an x squared from my first group. So I have a naught plus a1x plus a2x squared all the way up to an xn times x squared. And from this grouping over here, I also factor out an x squared. But this here is exactly t of p and over here we have t of q, and therefore additivity holds. Next, we consider homogeneity, so we look at t of alpha p. So here's t, and here is alpha times p. That's alpha times a naught plus alpha a1 x, all the way up to alpha a n x n. Taking the transform, then, I multiply this polynomial by x squared. The next steps, I essentially just pulled out the alpha. And in doing so, what I have here is alpha times my t of p, and therefore homogeneity holds. And since we have additivity and homogeneity, that means our transform t is linear. Our next example is the backward shift. So you want to recall the f to infinity. That's sort of like the generalization of f2, f3, f to the n, f all the way to the infinity. It's like an infinite vector, a vector of infinite length. So it denotes the vector space of all sequences of elements of f. We're going to define t to be a member of the linear transformations from f infinity to f infinity by t of x1, x2, all the way up to xn, or x infinity, is equal to x2, x3, all the way up to infinity. So essentially, you're shifting everything over and one space, so you get rid of the first element. A picture of what that looks like, here we have f infinity, so let's say we have the sequence of numbers 1, 2, 3, 4, all the way to infinity. Then we're going to map that by t, and what t does is it drops your first element. So actually this should be 2, 3, 4, 5, all the way to infinity. To show that our backward shift is linear, we're going to show additivity and homogeneity. I'm going to let x equal my infinite sequence x1, x2, x3 up to infinity. Y is going to be my vector with coordinates y1, y2, y3 up to infinity. For additivity, I look at t of x plus y, and x plus y is x1 plus y1, x2 plus y2, x3 plus y3 up to infinity. Then the transform, we get rid of our first term, so we have, I don't know why I missed x2 here. Let me rewrite this. So the transform shifts over 1, so we get rid of our first term and we get x2 plus y2, x3 plus y3, all the way up to infinity. Now, by vector addition, I can separate out my x vector from my y vector, right? So from here to here, it's just vector addition. But this here, the x2, x3 up to infinity, that's just t of x. And this here, the y2, y3 up to infinity, is just t of y. So we have shown that additivity holds. For homogeneity, we're going to consider t of alpha x. That's t of alpha x1, alpha x2, alpha x3. When we shift over, we're going to get alpha x2, alpha x3. I don't know why all of these I shifted over 2 instead of just 1, which is equal to alpha of times x2, x3 up to infinity, which is just equal to alpha t of x. So what we have is homogeneity holds, and since we have homogeneity and additivity, that means the backward shift is linear. This is either our last example or second to last example. So from Rn to Rm, let m and n be positive integers, and let a sub jk be a real number for j equal 1 to m and k for 1 to n, and then define t, our transform, to be a linear transform from Rn to Rm by t of x1, x2 up to xn, again it's a vector in Rn, is equal to a11 x1 plus a12 x2 up to a1n xn. This is the first coordinate. Then there's a second, third, until finally we get to the nth coordinate, which is am1 x1 plus am2 x2 all the way up to amn xn. And this notation isn't too bad, but one of the things about the 1, 1, 1, 2 up to 1n, and then presumably next we'd have 2, 1, 2, 2 up to 2n, all the way up to m1 to mn. This is suggestive of a matrix. So I find this easier to see like this. The transformation on an n-dimensional vector, this is t1 up to tn, is equal to this matrix of coefficients, over here, a11, a12, a1n, and then a21, a22, a2n, and then we go a31, a41 up to am1, am2, up to amn times our vector x1, x2 up to xn. And our matrix multiplication for this, we would multiply for this first coordinate, we multiply this row by this column, so we get a11 times x1 plus a12 x2 plus, and then all the way to a1n xn. Then our second coordinate is going to be the second row times this column. It's actually a linear combination of this row and column. So, or no, not a linear combination, but basically you make a linear combination of these x1, x2, xn by using these as the coefficients. So a21 times x1 plus a22 times x2 up to a2n times xn. And then for the final coordinate, I skipped a whole bunch, but the final one is going to be am1 x1, am2 x2, all the way up to amn times xn. So that's what this notation in your book is, how it's described, and it should suggest this matrix multiplication. And to be honest, I have an easier time seeing it this way. Over in this way, there's just too many, it's hard to even see where one coordinate ends and the next one begins. But I am going to start doing additivity using this notation here, and then I'll just do a quick, for some reason it's easier to see, maybe I'm cheating because I'm using the matrix and I know something about matrices, but we'll show what it looks like using the matrix kind of form. But we'll let x be one n-dimensional vector and y be a second n-dimensional vector. So x is equal to x1, x2 up to xn, y is equal to y1, y2 up to yn. For additivity, I want to see the transform on x plus y. So the x plus y vector has x1 plus y1 as its first coordinate, x2 plus y2 as its second coordinate, on up to xn plus yn as its nth coordinate. Doing the transformation then on this, that's going to be a11 times our first coordinate plus a12 times our second coordinate, which is x2 plus y2, all the way up to a1n times our nth coordinate, xn plus yn. So this is a linear combination, and that's our first coordinate after the transformation. There's going to be a second, a third, all the way up to the nth coordinate, and the nth coordinate is going to be am1 times x1 plus y1 plus am2 times x2 plus y2, all the way up to amn times xn plus yn. And this is where I think it looks ugly, but I multiplied my a11, my a12, my a1n. All of these are just scalars because it says over here a sub jk are real numbers. So these are just real numbers, they're scalars, so we can multiply them in, and that's what this line is. It's the a11 times x1 plus a11 times y1, and then the a12, all of these annoying terms, and then over here I multiplied out the am1 times x1, am1 plus y1, then I did it for am2 times x2, all the way out to amn times xn and amn times yn. Next, over here from my first coordinate, I grouped all my x's together and all my y's together. And then over here for my last coordinate, I grouped all my x's together and all my y's together. And now I used vector addition to separate out my y vector from my x vector. So my x vectors are in green, my y's are in yellow, so I group my x coordinates. My first coordinate here is the a11 x1, a12 x2 up to a1n xn. That's my first coordinate. And then I dot it all the way to my last coordinate, am1 x1 plus amn xn. Over here in yellow, I do the same thing. I group together my y coordinates starting with a11 y1 plus a12 y2 up to a1n yn. That's my first coordinate. Then I have a bunch of coordinates until this here is my last coordinate, am1 y1 plus all the way up to amn yn. And what you'll see is this here in green, that's just t of x. And over here what's in yellow is just t of y. So what we have is t of x plus y is equal to t of x plus t of y. So additivity holds. And next I'm going to work this problem in this matrix form as well. I just think it's easier to see. So here we have our x vector, our y vector. So our t of x plus y, we have our matrix of these real numbers, and then we have our x1 plus y1, x2 plus y2, up to xn plus yn. When I multiply this out, I have my a11 times my first coordinate x1 plus y1, a12 times x2 plus y2, and then I have my a1n times my xn plus yn. Next, I have my second row times my column, so a21 times x1 plus y1, a22 times x2 plus y2, all the way up to a2n xn plus yn, and I have the same for a31, a41, all the way up to am1 times x1 plus y1, am2 times x2 plus y2, up to amn times xn plus yn. What I can do now is I can group my x and my y terms. So here I've grouped my x terms, here I've grouped my y terms, right? I just multiply out the a11 scalar times x1, a11 scalar times y1. It's all added together. So I can then rearrange them. So my x's are together, my y's are together. X is together, y is together, all the way down to the nth row. X is together, y is together. So now I can separate them out. This part here, using, I should do it this way, using vector addition, this part here becomes my t of x, and this here becomes my t of y, and therefore additivity holds. So I've shown additivity, and now I still need to show homogeneity. So we're going to start with t of alpha x, which is t of alpha x1, alpha x2, up to alpha xn. Applying our transformation to alpha x1, alpha x2, and alpha up to alpha xn, we'll have a11 times alpha x1 plus a12 times alpha x2 all the way up to a1n times alpha xn. Our second line then will be a21 times alpha x1 all the way up to a2n times alpha xn. And then our final line is going to be alpha, I put the alpha on the outside here, alpha am1 x1 plus alpha m2 x2 all the way up to alpha amn xn. So on all of these, I can factor out my alphas, and what I get then is my alpha t of x, so homogeneity holds. Now with additivity and homogeneity, we can say our transformation is linear. And in particular, we can phrase this as any transformation, t, that goes from Rn to Rm, that can be represented by a matrix, is a linear transformation. Okay, back to our overview slide. So we just talked about our set of linear maps from vector space V to W. We have this theorem here that says linear maps and bases of domain. It says suppose V1, V2 up to Vn is a basis of V, and W1, W2 up to Wn are vectors in W. Then there exists a unique linear map, T, that goes from V to W such that T of Vj is equal to Wj. And somewhat related, and we're going to do an example of this, is the fact that once you know how a linear transformation acts on a basis of V, you know how the transformation acts on all the vectors at V. We will do an example, and for your reference, I put the theorem here. So suppose V1, V2 up to Vn is a basis of V, and W1, W2 up to Wn are vectors in W, then there exists a unique linear map, T goes from V to W, such that T of Vj equals W of j. Our example will be the 1, 0 and 0, 1 basis for R2. So if we know that the transformation T maps 1, 0 onto 3, 4, and the transformation T maps 0, 1 to 1, 2, what is the transformation of 5, 6? So in other words, given T of 1, 0 equals 3, 4, and T of 0, 1 equals 1, 2, how do we find T of 5, 6? Now remember, 1, 0 and 0, 1 is a basis, so we can write 5, 6 as a linear combination of 1, 0 and 0, 1. And also just looking at this theorem, remember V is a basis for the vector space V. The W1, W2, Wn, they're just vectors. They don't have to be a basis. The important thing is where you're starting from, your L of V, your domain, has a basis. So we're going to write our 5, 6 as 5 times 1, 0 plus 6 times 0, 1. By the additivity property of linearity, we know that t of the sum of two vectors is equal to the sum of t of the first vector plus t of the second vector. So we separate this out by additivity. Now by homogeneity, we can factor out the scalar coefficients 5 and 6. So we have now 5 times t of 1, 0 plus 6 times t of 0, 1, which gives us 5 times, and we know what t of 1, 0 is, that's 3, 4, plus 6 times t of 0, 1, which is 1, 2, which gives us the final answer of 21, 32. And looking at that, this is what this fact here is about. Once you know how a linear transformation acts on a basis of V, you know how the transformation acts on all the vectors in V. Because essentially all the vectors can be written as a linear combination of the bases. And then you use additivity and homogeneity to break it down. We are now on our last topic, which should go faster, which is the algebraic operations on our set of linear maps from V to W. First, we're going to define addition and scalar multiplication on our set of linear maps. Suppose S and T are linear maps from V and W, and A is a scalar. Then we can add our linear maps S and T, which we'll denote with S plus T, and we'll define that as the mapping that gives you the same results as S on V plus T on V. We will then define scalar multiplication, so scalar A times T, this new operator, then on V is equal to the scalar A times T of V. For an example of adding two linear operations, remember any transformation that can be represented by a matrix is a linear transformation. So I have two linear transformations here, T1 and T2. T1 can be represented by this matrix, A1, which is the matrix with columns 1, 2, 0, and columns 0, 1, 3. When you multiply this matrix times any vector x1, x2, because remember we're going from R2 to R3, you'll see what we get is this T1 transformation. That is my x1 plus 0x2 is my first coordinate, 2x1 plus x2 is my second coordinate, and 0x1 plus 3x2 is my last coordinate. Also, you can just notice that the A1 are just the coefficients in front of x1 and x2 in each row, right? So coefficient of x1 is 1, coefficient of x2 is 0, coefficient here are 2 and 1, and then coefficient of x1 is 0, coefficient of x2 is 3. Similarly, I have my transformation represented by matrix A2 with columns 0, 0, 3 and 1, 0, 1, and this represents this T2 transformation of x2, 0, 3x1 plus x2. Now I can add my two transformations, T1 plus T2. So I simply get x1 plus x2, my 2x1 plus x2 plus 0. And then my 3x2 here combines with this x2, so that's 4x2, and then I have my 3x1, or I can just add my two matrices. So I have 1, 1, and here I have 2, 1, and here I have 0 plus 3 is 3, and 3 plus 1 is 4. My next theorem is important. It says here, the set of all my linear transformations from V to W is a vector space with the operations of addition and scalar multiplication defined above. To show it is a vector space, we have to show all of these properties. I'm not going to prove this theorem, but I'm not even going to give you an example and go through all of these properties, but I will give you an example and go through a few of these properties. My example is going to be the linear mappings that we can represent with the matrix. So I have my first mapping T1 represented with my matrix A1, with columns 1, 2, 0, and 0, 1, 3, then my transformation T2, represented by my matrix A2 with column 0, 0, 3, 1, 0, 1. Now I can add my two matrices together, which is equivalent to adding the corresponding matrices together. So I'm going to get the matrix 1, 2, 3, and 1, 1, 4. And here's my actual transformation. We will use this example and illustrate a few of these, or just pick out a few of these to talk about. First, vector addition is closed. So when you have a transformation from R2 to R3, and you add it to another transformation from R2 to R3, because here we're talking about the space L where we go from the same domain to the same range. So these are both R2 to R3. So you can see when you add these matrices, or when you add these two transformations, you're not going to go out of the space R2 to R3. You can see that addition is commutative, because over here it really didn't matter if you did T1 plus T2, or if you did T2 plus T1, because that would just equal to, let's see, x2 plus x1, and then we still have the 2x1 plus x2, and then finally we would have the 3x1 plus x2 plus 3x2. But, because these are real numbers, it would just equal to T1 plus T2. You can kind of convince yourself that addition is associative. The additive identity, that's the transformation from R2 to R3 that maps everything into 0, 0, 0. And the matrix that represents this transformation is the 0, 0, 0, 0, 0, 0. You can go through these properties and you can kind of convince yourself that this is a vector space. Just make sure you're operating on the transformations themselves. Next, we define the product of linear maps. So if we have T and S, and they're both linear maps from V to W, then the product, S times T, is equal to, this actually looks more like composition, is actually the linear map defined by S of T of U. So it's exactly more like composition than multiplication. We'll do an example of that in a minute, but let me also give you one last theorem. Algebraic properties of products of linear maps. So if T1, T2, and T3 are all linear maps, then their product, as we just defined, obeys associativity laws as well as distributive laws here. Oh, and also there's an identity mapping. The example we have for products of linear maps is, suppose D is an element of the linear maps from the space of polynomials to the space of polynomials, and D is the differentiation map. So we looked at that in a previous example. So when you have a polynomial, D will take the derivative to give you a new polynomial. Let's say T is an element also of a mapping from polynomials to polynomials, and it's the multiplication by x squared map, and we also did this in a previous example. So show the product of linear maps is not commutative. Using then my definition of product, so we want to show that TD of P is not equal to DT of P. So in other words, we can't just commute the order of maps in our product of linear maps. So starting here on the left-hand side, we had TD of P of x. This is our product of two linear maps. By our definition, our product of two linear maps is S of T of U. So that's going to be T of D of P over here. So we do the first transformation D on P. So that's the derivative. So what we're going to get for D of P is P prime of x. Now the next step is do the transformation T on P prime of x. Well, the transformation T multiplies by x squared. So our final answer for TD P of x is x squared P prime of x. Now we want to compare this to DT P of x. So just rearranging the order of the product. So DT P of x using this rule here, that means we do d of t of p of x. So d of t of p of x. So we operate on p of x with t first, and we get x squared p of x. Then next we need to take the derivative. So remember we have to use the product rule because we have a product of two functions of x. So first we're going to have x squared times p prime of x plus 2x times p of x. So here I just pointed out we're using the product rule. So what you see in particular is this TD p of x is not equal to dt p of x. In other words, this product of maps is not a commutative product. Our final theorem for this video is linear maps take the zero vector to the zero vector. Our proof is T of our zero vector. So our zero vector, we can just add another zero vector to it. So 0 plus 0 is still our zero vector. So T of our zero vector is equal to T of 0 plus 0. By our additivity, because this is a linear map now, we get, because our assumption is that we're talking about linear maps, is we can separate this out to T of 0 plus T of 0. So taking this far left-hand side, equating it to the right-hand side, we get T of 0 is equal to T of 0 plus T of 0. I'm going to subtract minus T of 0 from both sides of this equation. So from over here, I'm going to say minus T of 0, and that's going to give me 0. Over here, I'm going to subtract a minus T of 0, and that gives me one single T of 0. So you can see T of 0 is equal to the 0 vector. And that was our last theorem. So to review what we talked about in this video, we talked about the vector space of linear maps. The first thing we did was define a linear map, or also known as a linear transformation, from a vector space V to a vector space W is a function t going from V to W with the following properties. What makes it linear is one, it has an additivity property, so that t of a vector u plus v is equal to t of u plus t of v. It also has a homogeneity property, which says t of alpha, where alpha is a scalar, times v is equal to alpha t of v. And we did several examples, and we showed additivity and homogeneity, and we also did examples of functions that were not linear. We said the set of all linear maps from V to W, we would notate that with the script L, L for linear. So linear maps from V to W, this is a set of mappings. Then we said that linear maps and bases of domain. So suppose we have V1, V2 up to Vn as a basis of our domain. Then W1, W2, Wn are vectors in our range W. Then there exists a unique linear map, T of V to W, such that T of V sub j is equal to Wj. And we use this in an example, and it illustrates that once you know how a linear transformation acts on a basis of V, you know how the transformation acts on all vectors in V. And finally, we talked about algebraic operations on our space of all linear maps. We defined addition and scalar multiplication on these linear maps. And then with those operations of addition and scalar multiplication, we said that the set of all linear maps from V to W is a vector space. So this is important. All linear maps from V to W is a vector space. We talked about products of linear maps, which looks a lot like function composition. And then we talked about the algebraic properties of linear maps. And then finally, we said for a linear map, it'll always map the zero vector to the zero vector. So that's it for this video. Thank you for watching.